Hello and welcome to Algebra 2 Lesson 58. In this video, we're going to learn about rationalizing the denominator. So for the majority of you, you took Algebra 1 before jumping into this Algebra 2 course. And I know most of you have seen rationalizing the denominator before. But again, when you get into Algebra 2 or even college algebra, there's just a lot of topics that you go over again. So it's not something that you should be bored with. Take the time to, again, cover this again and make sure you have a complete understanding of it. And if it's something you're seeing for the first time, this is not something that's super difficult. Some of the examples will get a little bit challenging though. All right, so let's start off with something kind of simple. So we have 5 times the square root of 3 over the square root of 2. So the first question we would ask is this simplified? So I would relate this to when we work with fractions. If we had something like 3 over 12, we didn't report that, right? We wanted to simplify this and say, okay, well, 3 divided by 3 is 1, 12 divided by 3 is 4. So the simplified answer here would be 1/4, right? This is simplified. But mathematically, these two have the same value, okay? They're both equal to 0.25 in decimal form. It's going to be kind of a similar experience over here. Our rule is we don't want a radical in the denominator. So here we have the square root of 2, which is a radical. So in order to simplify this, what we do is a little trick. We're going to multiply the numerator and denominator by the square root of 2. Now, what's that going to do for us? The square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. So what we did is we took an irrational number, like the square root of 2. Let me write that this is irrational. And we made it into a rational number, which is 2. Henceforth, the term rationalizing the denominator. We go from an irrational number that's a denominator to a rational number that's our denominator. Now, I can't just do something to the denominator without doing the same thing to the numerator. Remember, just like when we work with fractions, same non-zero number over itself is 1. So this has a value of 1. And if we multiply by 1, something is unchanged. So you'd essentially have 5 times square root of 3 times square root of 2. So we'd have 5 times square root of 3 times square root of 2, which simplifies to 5 times the square root of 6. So some of you will say, well, how come there's a radical in the numerator? Why is that allowed? The reason for this is when this rule was invented on how to simplify a radical, they didn't work with calculators. Now, I can take this guy right here and this guy right here, and I can punch it up on a calculator in an equal amount of time. If I didn't have a calculator, this one right here on the left, this guy would take longer to calculate than this guy. Now, the rule has still stuck around, and you're expected to know how to do this in almost every math class, so it's something you just need to learn how to do. But mathematically, this guy right here and this guy right here, they have the same value. It's just like when we looked at 3/12 and 1/4, right? They are the same mathematically. One is simplified, one is not. All right, let's take a look at another. So suppose you see something like this, 4 times square root of 9 over 2 times square root of 6. Well, the first thing is, you know you can cancel this 4 with this 2, right? 2 divided by 2 is 1, 4 divided by 2 is 2. So this would turn the problem into 2 times the square root of 9 over the square root of 6. Now, the next thing is the square root of 9 is 3. So we can go ahead and simplify that and say we have 2 times 3, which is 6, over the square root of 6. Okay. Now, in order to report a simplified answer, we don't want a radical in the denominator. So again, we're going to use our little trick. We're going to multiply this by the square root of 6 over the square root of 6. And what's going to happen is you'll have 6 times the square root of 6 over square root of 6 times square root of 6 is what? It's 6, right? It would be the square root of 36. Square root of 36 is 6. Now, between the numerator and denominator, I can cancel a common factor of 6. This is multiplication here, so I'm canceling common factors. And what we're left with is simply the square root of 6. All right, let's take a look at another one. So we have 4 minus the square root of 5b squared over 5 times the square root of 15b cubed. So a lot of things to simplify first. You always want to think about what can I simplify. So we have 4 minus. Now, this right here, you think about b squared. The square root of b squared is nothing more than b. Again, a quick way to do that is with exponents. If I have b squared, and I'm taking the square root of that, so this is like raising something to the 1/2 power, you do power to power rule here. You have b raised to the power of 2 over 2, which is just b to the first power, or b. What's going to happen is, I'm going to pull a b outside, and then it'll be times the square root of 5. And this is over. Down here I have 5, which is multiplied by, you've got 15b cubed. Now 15 is 5 times 3, so I can't really do anything with that. So that would stay underneath. But with b cubed, again, if this guy right here is equal to or greater than the index, you know you can simplify that, right? I can separate that up into b squared multiplied by b. So if I wanted to go kind of a long way about this, I could say this is the square root of b squared times the square root of b. This guy right here is b, so that could come out, and I could erase this. And if I'm multiplying by the square root of b, I could just write this underneath. So we've simplified that part as much as we can. But again, in the denominator, there is a radical. So I'm not going to multiply by the entire denominator. I'm just going to multiply by what I need to get rid of that radical. So let's start that down here. We have 4 minus b times the square root of 5 over 5b times the square root of 15b. Now what I'm going to do, I'm going to multiply the numerator and denominator by this guy right here. So the square root of 15b over the square root of 15b. Now, there's a minus sign here. If I'm going to do this properly, I'm going to use my distributive property. This is going to be multiplied by this, and then it's going to be multiplied by this. So you'd have the square root of 15b multiplied by 4. So 4 can just go out in front. Then minus, I've got b times the square root of 5 times the square root of 15b. So b is out in front times the square root of 5 times the square root of 15b. And this can be simplified further, but we'll do that in a minute. So this is over. Now down here, I've got this 5b multiplied by, you have the square root of 15b times the square root of 15b, which is just 15b. Okay, so let's further simplify now. So in the numerator, we have 4 times the square root of 15b. Nothing I can really do with that. 15 is 5 times 3. b is just b. Can't really do anything. Then minus. Then for this guy right here, I have b times the square root of 5. Then I'm going to break this up into the square root of 5 times the square root of 3 times the square root of b. Now, square root of 5 times square root of 5 is 5. So I might as well just erase this and put 5. And then there's really nothing else I can do with the rest of that. So if I want to clean this up, I can put minus 5b times the square root of 3b times the square root of 3b. Then this is over. You've got 5b times 15b. Really all I can do is say that's 75b squared. The last thing I want to do is see if there was anything that would cancel between numerator and denominator. Remember, you've got subtraction here. This is not multiplication. So I would have to factor something from both terms in the numerator. I'd have to factor something out to see if it would cancel here. So when I look at this, there's not really anything I could do that would make an impact. Some of you will say, well, in the numerator, you could factor out the square root of 3b. You could, but there's nothing to cancel that with down here. So this would be as simple as we can make this. All right, let's take a look at another one. So we have 2 plus 3 times the square root of 5v over 2 times the square root of 20v to the 4th power. So in the numerator, nothing really to simplify. So just 2 plus 3 times the square root of 5v. Now in the denominator, we have 2 times, for the square root of 20v to the 4th power, we'll break that up into the square root of 4 times the square root of 5 times the square root of v to the 4th power. So we can do some simplifying now. 2 plus 3 times square root of 5v over the square root of 4 is 2. So 2 times 2 would be 4. So let's put a 4 out in front. Then the square root of v to the 4th power is v squared. So let's put a v squared next to that. And then we're left with this square root of 5. So this is pretty easy to clean up. I have a radical in the denominator that I want to kind of get rid of. So all I'm going to do is multiply the numerator and denominator by that square root of 5. All right, so what's going to happen? Again, I've got to use my distributive property because I have this plus here. So square root of 5 times 2 is just 2 times square root of 5. Then plus the square root of 5 multiplied by 3 times the square root of 5v. You can really say this is 3 times square root of 5 times square root of 5 is 5. So 3 times 5 would be 15. So let's just write 15. And then the thing that would be left would be the square root of v. Okay, so times the square root of v. Then over, down here, square root of 5 times square root of 5 is 5. 5 times 4v squared would give us 20v squared. You're looking, if you want to cancel here, because there's this plus sign, you'd have to factor something out from both these terms here to be able to cancel it with something in the denominator. We don't really have anything. You have 2 and you have 15. You have square root of 5 and you have square root of v. So nothing really I can pull out there that I could cancel with that 20v squared. So this is simplified. 2 times square root of 5 plus 15 times square root of v over 20v squared. All right, so now let's talk about something that's a little bit more complex, which is dealing with this when we have higher level roots. So when we get to higher level roots, we need to pay attention to what is needed. We think about something like this. We have 3 times the cube root of 4r squared over 5 times the cube root of 25r. This is one thing that you really got to pay attention to. So you're looking at this and you're saying, okay, I want to simplify this. A lot of students will just start out and go, okay, you know what? I'm going to multiply this by cube root of 25r over cube root of 25r. Now, 25 times 25 is 625. That is not a perfect cube. It's a perfect fourth, but not a perfect cube. So again, when you see something like this, you want to factor things and kind of think about stuff. So in the numerator, there's nothing really I can do to simplify. So 3 times the cube root of 4r squared. We know 4 is a perfect square, but not a perfect cube. R squared is a perfect square, but not a perfect cube. So we move on to the denominator. We have our 5, and then we're going to break this up. So times the cube root of 5 times the cube root of 5. 5 times 5 is 25. And then times the cube root of r. So you're thinking about how you could get a perfect cube there. You've got 5 times 5 there. You just need another 5 to get a perfect cube. 5 times 5 is 25. 5 times another 5 would be 125. That's a perfect cube. So when you do this, you want times the cube root of 5. But you also have to think about this r here. You have the cube root of r. You need to make that a perfect cube also. So if you just have r to the first power, you're going to need to multiply that by r squared so that you can get r cubed and have a perfect cube. So we would add under here r squared, and you do the same thing in the numerator and the denominator. So this is how you go about setting these things up. Especially when you get into these higher level roots, you want to take the time to break things up and see what's needed. If you don't, you might end up costing yourself a lot of extra time, or you might just outright get the wrong answer. All right, so let's go through and multiply. So in the numerator, we'll have 3, which is multiplied by the cube root of 4r squared times the cube root of 5r squared. So this would be the cube root of 4 times 5, which is 20, times r squared, which is r to the 4th power. Of course, we can simplify this, and we'll deal with that in a second. Over, we'll have 5 multiplied by, we'd have 5 times 5, which is 25, times another 5, which is 125. So it would be the cube root of 125, which is 5, so 5 times 5. And then you'd end up with the cube root of r cubed, which is r. So my denominator is radical free. So in the denominator, we would basically just have 25r. In the numerator, you'd have 3 multiplied by 20 is what? It's 5 times 2 times 2. There's no perfect cubes in there, so you can just leave that 20. So we'll put the cube root of 20 multiplied by, when we think about the cube root of r to the 4th power, we know we can simplify this. Again, if the exponent here is the same or greater than the index, you can simplify. You could split this up into the cube root of r cubed multiplied by the cube root of r. This right here is just r, so I could put an r there. And then I can get rid of this, and then this r can go underneath here. Now, before I conclude my problem, this is multiplication here, so I don't need to factor anything. I can just cancel, right? I can cancel common factors. This r with this r, and end up with 3 times the cube root of 20r over 25. All right, for the next one, let's take a look at 5 times the 4th root of 3x to the 4th power over 3 times the 4th root of 75x cubed. So when we look at this in the numerator, if we have x to the 4th power, we're taking the 4th root of that, we know that's just x. So we can simplify that to start and just say I have 5x, right? I just pulled this out, times the 4th root of 3. Okay, then this is over. We have 3 multiplied by, we have the 4th root of 75x cubed. Now, x cubed is not a perfect fourth, so we can't do anything with that. And 75 is not a perfect fourth. But again, we're going to think about what we'd need to do to get a perfect fourth. So 75 is what? It's 5 times 5, which is 25, times 3. And then x cubed is x times x times x. So I know to get a perfect fourth here, I just need one factor of x, right? That's it. One more factor of x, we'll be good to go there. For this guy, I need 2 factors of 5, and I need 3 factors of 3. So that's 5 times 5, which is 25, times 3, which is 75, times 3 again, which is 225, times 3 one more time, which is 675. So we'll need to multiply this by the 4th root of 675 and then x. Okay, we'll do that to the numerator and denominator. All right, let's erase this and let's crank this out. So we'll have 5x multiplied by the 4th root of 3 times the 4th root of 675x over, you'll have 3 multiplied by the 4th root of 75x cubed times the 4th root of 675x. We know the 4th root of x to the 4th power would just be x. So let's just do that first. 75 times 675 ends up being 50,625. But we don't need to think about that because we built this by looking at the prime factors. We remember it was 5 times 5 times 3 to get to 75. So I only used 2 prime numbers in this. I used a 5 and a 3. So basically this number that we end up with is 5 to the 4th power times 3 to the 4th power. Or in other words, it's 15 to the 4th power. So the 4th root of 15 to the 4th power is just 15. So times 15. 3 times 15 is 45. So let's write this as 45x. Now before we do anything else, we notice that 5 would cancel with 45. This would be a 9. And x would cancel with x. Now, what are we left with now? If we look in the numerator, we've got the 4th root of 3 multiplied by the 4th root of 675x. So we know we're not going to be able to do anything with this, but when we think about 675, that came from 2 factors of 5, or 25. And it came from 3 factors of 3, or 27. So we look through here, and we look for a perfect fourth. Let me put times the 4th root of x, just so we don't forget that. So we would have what? 1, 2, 3, 4 factors of 3, or 81. Let me just complete this. I'm going to put over 9. So you would have the 4th root of 81 times the 4th root of 5 times 5, or 25, times the fourth root of x over 9. This right here has a value of 3. So you basically have a 3 here. So I could cancel this with this and leave a 3. And as my answer is going to go, we would end up with the fourth root of 25x over 3. All right, so for the next one, we have 5 times the cube root of 2n to the fourth power plus 3 times the cube root of 3n over 5 times the cube root of negative 6n. So what we want to think about here, we have 5 times, let's break this up a little bit. We know if we see an index of 3 and an exponent of 4, we can do something there. So let's say we have the cube root of 2 times the cube root of n cubed times the cube root of just n plus 3 times the cube root of 3n over, we have 5 times the cube root of, I'm going to split this up into negative 1 times the cube root of 6n. This can be simplified and this can be simplified. So what we want to do, we'll have 5 times the cube root of 2. This would end up being what? This would end up being just n. So I can just write this n out in front. Let me just kind of slide this down a little bit. And then times, you'll have the cube root of n. And then plus, you have 3 times the cube root of 3n. And then over, this again can be simplified. The cube root of negative 1 is just negative 1. So I'd put negative 5 out here times the cube root of 6n. Well, down here, again, we don't want this radical in the denominator. So what we want to do, we think about 6. 6 is 2 times 3. So really, I'm not going to get it any more simple. N is just n. So if I have 6n, all I'd want to do is multiply this by 6n, that amount squared, or 36n squared. That would give me a perfect cube. It would give me 216n cubed, which is a perfect cube. So we'd multiply the numerator by the cube root of 36n squared, and the denominator by the cube root of 36n squared. And what are we going to get? Again, if I kind of combine this to make it a little easier, put this n underneath, then this would get multiplied by this. So you'd have 5n out in front, multiplied by the cube root of 2n times 36n squared. 36 times 2 is 72. N times n squared is n cubed. Then plus. This is going to multiply by this now. So you'd have 3 out in front. The cube root of 3n times the cube root of 36n squared. You would have the cube root. 3 times 36 is 108. N times n squared is n cubed. All right, then this is over. Down here, you're going to have negative 5 out in front. And again, the cube root of 6n times the cube root of 36n squared is going to give you what? It would be the cube root of 216n cubed, which would basically be 6n. So negative 5 times 6n would be negative 30n. And now we're just looking to see, can we simplify anything further? So before we try to factor anything, in the numerator, let's think about 72 for a second. 72 is what? It's 8 times 9. We know 8 is a perfect cube. It's 2 times 2 times 2. 9 is not. It's 3 times 3. So what we could do is we could write this as 5n times the cube root of 8 times the cube root of 9 times the cube root, when we think about this right here, this n cubed, the cube root of n cubed. So these two can be simplified. The cube root of n cubed is n, so we can just make this n squared. And the cube root of 8 is 2, so we can just make this 10. So we get 10n squared times the cube root of 9. Then you're going to have plus. Over here, we think about 108. Now, what is 108? It's divisible by 2. It's also divisible by 3. So we know it's divisible by 6. So let's factor it and say, if I divide 108 by 6, I would get 18. 6 is 3 times 2. 18 is 6 times 3. 6 is 3 times 2. You've got 1, 2, 3 factors of 3 and 2 factors of 2. So it's essentially 27, which is a perfect cube, times 4. So we can say this is 3 times the cube root of, let's just go ahead and do 27n cubed times, we'd have the cube root of 4. Now again, this part right here can be simplified. The cube root of 27n cubed is going to be 3n. So 3n multiplied by this 3 that's already here would give us 9n. So this would be 9n multiplied by the cube root of 4. Then over, we'll have negative 30n. Now, here's the question. Again, because this is addition, can I factor anything out and then cancel? Well, number-wise, the answer to that is going to be no. 10 is 5 times 2, 9 is 3 times 3. Nothing I can really do there. But variable-wise, yes. I have n squared and I have n. So I could factor an n out, and I'd have 10n times the cube root of 9 plus 9 times the cube root of 4 over negative 30n. Then this would cancel with this, and what I'm left with, we'd have 10n times the cube root of 9 plus 9 times the cube root of 4, and then this is over, we'd have negative 30. Right? So this would be our answer.